Section: Introduction. In this section, we introduce self-supervised pre-training, which has significantly changed machine learning by enabling the creation of foundational models in both vision and language. These models, characterized by their large number of parameters and extensive training on vast datasets, often develop strong general-purpose abilities during pre-training. However, while these models excel at static tasks, adapting them to new and evolving data, like fresh text or new visual concepts, poses a significant challenge. This difficulty arises mainly from the high costs of retraining and the risk of catastrophic forgetting when faced with major changes in data distribution. Recent studies have suggested methods for continual pre-training in language models, but we find that systematic approaches that fit well into existing pre-training processes are still missing. In computer vision, traditional continual learning methods, such as regularization and architectural changes, struggle to scale with modern foundational models. This is due to two main issues: their inability to adapt to self-supervised learning goals and large datasets, and the limitations they impose on model architecture, which may not suit the variety of current models. Most continual pre-training methods use a repeated cosine annealing schedule with a set duration. This approach assumes a fixed endpoint in training, which restricts future pre-training on new datasets and leads to significant forgetting. This limitation prevents true continuous adaptation, as traditional learning rate schedules tend to decrease to very low values, hindering further meaningful updates. Additionally, rewarming the learning rate from its lowest point can cause instability and worsen forgetting. To address these issues, recent research has looked into more flexible infinite learning rate schedules that can adapt to different training lengths. While these innovations have mainly come from data scaling studies, they are starting to be applied in continual learning contexts. However, a crucial question remains unanswered: how do these scheduling methods perform when faced with distribution shifts, particularly with non-IID data? This is especially important for real-world applications where models need to adapt continuously to data from various domains. For example, continually pre-training an English language model to include German presents a challenge, as catastrophic forgetting can significantly degrade performance. In our work, we tackle this question by thoroughly examining the role of learning rate schedules in self-supervised continual pre-training. Through extensive experiments in both vision and language, we believe we are the first to compare infinite learning rate schedules with repeated annealing in detail. Our findings indicate that infinite schedules effectively manage catastrophic forgetting in non-IID settings, preserving model performance across diverse data distributions. We make several key contributions. We present the first systematic study on the effects of learning rate schedules in non-IID self-supervised continual learning for both vision and language. We show that infinite learning rate schedules, both alone and in combination with experience replay, outperform several advanced continual learning methods. And we demonstrate that, across various large-scale sequential pre-training tasks, infinite learning rate schedules surpass repeated cosine annealing. Our results suggest that the infinite cosine schedule should be the standard for continually pre-training foundational models, as it enhances knowledge retention compared to repeated cosine schedules in challenging non-IID self-supervised learning scenarios. In the related work section, we discuss continual pre-training of vision foundation models, which aims to adapt vision transformers to sequential data while reducing catastrophic forgetting. We also review continual pre-training strategies for large language models, highlighting their ability to retain knowledge across tasks. Furthermore, we explore alternatives to the cosine schedule, noting that while some advancements allow for continuous training, they primarily address data scaling rather than distribution shifts. Our research builds on this by examining pre-training under explicit distribution shifts and expanding the framework to vision foundation models through masked image modeling approaches. Section Summary. In this section, we discuss the challenges of adapting self-supervised foundation models to evolving data, particularly the issues of catastrophic forgetting and the limitations of traditional learning rate schedules. We present our findings that infinite learning rate schedules, particularly the infinite cosine schedule, effectively mitigate forgetting in non-IID settings, outperforming conventional methods in continual pre-training across both vision and language modalities. Section: The need for infinite learning rate scheduling, why it matters. In this section, we discuss the importance of infinite learning rate scheduling, particularly in the context of training large-scale models. We note that cosine scheduling has been the standard method, effectively balancing high learning rates for quick optimization with gradual reductions for stable convergence. However, this method requires prior knowledge of the total number of training iterations, which limits our ability to continuously train models on new data. We explore alternatives like infinite learning rate schedules and warm-up stable decay, WSD, which allow for training without needing to set a specific number of steps in advance. These methods naturally support continual learning and offer the added benefit of rapidly decreasing the learning rate towards the end of training. This sharp reduction can significantly lower the loss, enabling us to save model checkpoints just before this decay for future training cycles. This is especially useful when we need to deploy the best model while expecting more high-quality data later. We investigate the effectiveness of the infinite cosine schedule compared to the traditional cosine schedule for continual pre-training of models facing significant distribution shifts. Our experiments cover various self-supervised learning tasks in both vision and language fields. We demonstrate that infinite learning rate scheduling not only improves robustness against distribution shifts but also serves as a superior alternative to cosine scheduling by removing the need to predefine training duration. We define the infinite cosine schedule, where the current training step, maximum and minimum learning rates, and the number of warm-up, cooldown, and decay steps dictate the transitions between phases. The learning rate increases linearly during the warm-up phase, then follows a cosine cooldown until a certain point, remains constant for a while, and finally decreases exponentially towards the end of the task. For continual pre-training, we can easily resume from the pre-annealed checkpoint at a constant learning rate, avoiding the need for rewarming. Our experimental setup includes both vision and language domains, focusing on significant distribution shifts across multiple datasets. We first test the infinite schedule on a small-scale masked autoencoders, MAE, pre-training, comparing it to continual learning baselines. We then scale up to larger vision datasets with notable distribution shifts and demonstrate its applicability by continually pre-training large language models across various distributions. For our MAE continual pre-training, we utilize masked autoencoders, which align well with language models and excel in masked image modeling. We conduct experiments on CIFAR10, dividing the dataset into 5 sequential tasks with 2 classes introduced in order. We use a VIT tiny model and train for 400 epochs with a specific batch size. We compare our approach against several continual learning baselines, adapting them for self-supervised pre-training. These include sequential fine-tuning, experience replay, memory-aware synapses, learning without forgetting, and GDUM. For evaluation, we employ standard continual learning metrics such as average accuracy, forward transfer, and backward transfer. Section Summary. In this section, we discuss the advantages of infinite learning rate scheduling over traditional cosine scheduling, highlighting its flexibility for continual training without needing predefined iteration counts. Our experiments demonstrate that the infinite cosine schedule enhances robustness to distribution shifts and allows for efficient model checkpointing, making it particularly beneficial for scenarios where models must adapt to new data continuously. Section: Large-scale MAE pre-training across multiple distributions. In this section, we describe our large-scale pre-training approach for masked autoencoders, MAE, across various datasets. We utilize 3 carefully chosen large datasets. First, we start with ImageNet, which contains 1.28 million images of objects across 1,000 categories, laying the groundwork for object recognition. Next, we shift to the Places 2 subset, featuring 1 million images for scene understanding across 365 categories. Finally, we incorporate the Fire Risk dataset, which includes 91,000 satellite images for environmental monitoring, marking a significant transition to remote sensing. This sequence of datasets enhances the distribution shifts from object recognition to scene understanding and then to aerial imagery. For evaluation, we assess both task-specific performance and the transfer of knowledge across tasks using a method called linear probing. After pre-training on each dataset, we freeze the feature extractor and train a linear classifier for each task, optimizing it with cross-entropy loss and measuring accuracy on specific validation sets. In terms of implementation, we build on the PyTorch May framework using a VIT-B16 backbone. We maintain a constant learning rate for the infinite schedule while the baseline follows a cosine decay schedule. Our experiments include variations with and without a replay buffer, and we train all models for 300 epochs per task using AtomW with a batch size of 4096. For continually pre-training language models, LLMs, we consider 3 datasets: DCLM baseline, stack, and German. DCLM is a large natural language dataset, stack consists of programming snippets, and German is part of the multilingual Oscar corpus. We selected stack and German to represent realistic distribution shifts, allowing us to evaluate the model's adaptability to new tasks. We tokenize all datasets using the Llama 3 tokenizer, which has a large vocabulary. We sample a small subset of tokens from each dataset for our experiments, being mindful that as the domain shifts, the tokenizer may become a performance bottleneck. In our implementation, we compare the infinite cosine schedule with the standard cosine plus warm-up schedule, fixing certain parameters while varying others. We use the Llama 3 architecture with 570 million parameters, training it as an autoregressive transformer with a causal language modeling objective. Our results for pre-training May on CIFAR10 show that the infinite cosine schedule outperforms the standard cosine schedule, achieving higher average accuracy and backward transfer across all tasks. Specifically, without experience replay, we see an improvement in average accuracy and backward transfer compared to fine-tuning with a repeated cosine schedule. Interestingly, using experience replay in this setup actually degrades performance, likely due to limited data diversity leading to overfitting. In contrast, the infinite learning rate schedule avoids these issues. Overall, our findings indicate that the infinite cosine schedule consistently outperforms baselines, and larger replay buffers enhance performance, suggesting our method scales well for large-scale pre-training. Section Summary. In this section, we describe our large-scale May pre-training approach using 3 diverse datasets, transitioning from object recognition to scene understanding and remote sensing, and evaluate performance through linear probing. We also highlight the effectiveness of the infinite cosine learning rate schedule over standard methods, demonstrating improved accuracy and backward transfer, particularly in small-scale continual pre-training scenarios. Section Discussion. In this section, we examined various hyperparameters of the infinite cosine schedule in our extensive experiments involving both vision and language tasks. When we did not use replay, we found that a lower constant learning rate, referred to as eta constant, generally led to better performance in both areas. However, when replay was included, we noticed a clear difference. Vision tasks continued to prefer a lower eta constant, while language tasks showed improved results with a higher eta constant. The difference in performance for vision tasks between high and low eta constant was significant, about 10 times, while for language tasks, the variation was smaller. This indicates that comparing eta constant across these 2 modalities isn't straightforward, as their sensitivity scales differ. Therefore, we conclude that selecting the optimal constant learning rate requires careful tuning of hyperparameters, which we recognize as a limitation of our study.